Some of the homework tonight's going to need to be drawn on some graph paper. Okay, so there'll be a submission button in Canvas, so make sure that you do put these onto graph paper for me. If you want to do the whole rest of the assignment on like the bottom of that and turn the whole thing in digitally, that's fine. If you'd prefer to do the non-graphing questions on notebook paper, that's fine too, and just do half and half. Okay.
So you just need to do all the graphing digitally?
Yes, that would be my preference. Yes, easier for me to grade that way. Okay, so what you're going to do is you're going to be given an analysis chart that's already done. And from that analysis chart, they're going to ask you to create a continuous function that meets all the criteria on the analysis chart. All right, so let's just practice that together and see how that would go. All right, so suppose you know, or you're given a continuous f of x with even symmetry. Okay, so you're told it's continuous. What are you intentionally not told? Okay, you're not told it's differentiable, which means there could be corners, cusps, or vertical tangents. So that's fine to have that in the creation of your drawing. Okay, your drawing would reflect the following intervals. All right, 0 to 1. 1 to 2, and 2 to 3. In those intervals, you would be told enough information about what the first derivative was doing and what the second derivative was doing. And you have to imagine those little sticky note pieces that we had in class yesterday and try and put together a graph that meets all of that criteria. Okay, so the derivative is minus, minus, plus. The second derivative is plus, minus, minus. And it'd be really helpful if you had some initial conditions or some actual physical points that your graph needs to go through. And so you'll often be given at least one point, if not multiple points that you need to consider. And so you'll be given in this one, it needs to go through the point 0, 2. It needs to go through the point 1, 0. And it needs to go through the point 2, negative 1. And so then your job would be to create something that meets all of those criteria. A continuous function with even symmetry that goes through those following points that also has the plus minus things that you need. Okay, so let's start with the fact that it has even symmetry. Even symmetry means everything on the right side of the y-axis would be exactly reflected on the other side of the y-axis. And so if we have some points that are given, we can assume that by symmetry there are some points on the other side of the x-axis that would also be true. And so let's sketch our graph here and give yourself enough, enough space. And we're going to spread these out. So we know that 0, 2 is a point on our graph. We know that 1, 0 is a point on our graph. And we know that 2, negative 1 is a point on our graph. But if this has even symmetry, then there are also some points that exist in quadrants 2 and 3 that we can assume should be there as well. And so the reflected points, there should be a point here at negative 1, 0, so we'll add that to the list. And there should also be a point at negative 2, negative 1, so we'll add that to the list. Okay, that comes from having even symmetry. It also means that your chart should have reflected symmetry as well. So you can take this chart here and extend it out the other direction. So I should have told you to leave some space for that, but we can take our chart and work it backwards. And we should have a chart that goes from -1 up to 0. And we should have one that goes from -2 to -1. And we should also be able to go all the way back to -3 to -2. And the symmetry should be reflected. And so if the first derivative went minus, minus, plus out to the right, it should also go minus, minus, plus out to the left. Excuse me, should be reflected. I have to say, I did it exactly opposite of what I meant to say. The reflection should be plus, plus, minus, okay? The direction should be exactly reflected as well. Okay, the concavity does not reflect. That's where it's the same. Plus, minus, minus. Things that are concave up are still concave up when you reflect them over the y-axis. But things that are increasing are decreasing when you reflect them. All right, so let's see if we can create a drawing from that. So our first segment is going to connect -3 to -2. It needs to, if I'm looking at that combination, I'm looking at that segment right here, it needs to be a function. Did I have it right the first time? Now I'm like totally second guessing myself. Time out. Yeah, we're fine. It's because I did not put a mark for -3 on my graph. That's where I was getting off. Okay. Going from -3 to -2, we need to have a decreasing segment that also has negative concavity. Okay, a decreasing segment that has negative concavity, and then I'm going to hit what's green right now, -2, -1. And so my graph is going to look like this. There we go, line that up so it doesn't go past -3. Okay, a decreasing graph that has negative concavity. You could draw it lots of ways. If you just want to make it, look like this, or it could look like this, or it could look like this. You could have lots of things that are decreasing with negative concavity. Just pick your favorite shape that meets that criteria. It in fact could be a really low one. It could be like this, decreasing with negative concavity. Doesn't matter as long as it meets the criteria. Okay, the next 2 points from -2 to -1. We now know that that has to have an increasing slope, but also have negative concavity. So an increasing slope with negative concavity looks like this. Come on. There we go. Okay, that's increasing slope, and that has just created our first, bless you, our first cusp. Increasing slope, negative concavity. We also have a min. Next, from -1 to 0, I switch to a positive slope with positive concavity. And so the slope is not changing in nature, it's still positive, but the concavity does. And so to have a positive slope with also positive concavity, it's going to look like that. And so that's just created for me an inflection point, because the slope value didn't change, the slope nature didn't change, but the concavity nature did. Now the other side of the graph should be exactly reflected of what we just created. So from 0 to 1, I'll have a negative slope with positive concavity, followed by a negative slope with negative concavity, followed by a positive slope with negative concavity. And you should have created a picture that has perfect even symmetry with all the different concave pieces. And you should be able to identify, what's what and argue your way through it. So right here, these two are our 2 inflection points. You would state your case for those being inflection points because the concavity changed. F double prime of x changed. you should be able to identify these 2 points down here as our mins. And you would state your case for that because f single prime changed in a particular way, and it changed from negative into positive. That's why those qualify as mins, because of the change that happened there. And then you could state your case for our only max, and that's our only max because f single prime changed. It's the only place where we change from positive to negative. And so you argue your case for that. Okay, any questions about that so far? Okay. All right, last thing. I'm going to give you an alternate way, which is just as valid, to prove a max-a-min. Okay, this way only works if it's with a 0, coming from 0, not coming from undefined. Okay, so this is, it works in some cases, but not in all cases. Okay, so let's say that you find your critical points in the first derivative. Okay, you found your critical points in the first derivative. And let's remember what those two categories are. The critical points in the first derivative, aside from the endpoints, the critical points in the first derivative would be set f prime equal to 0 or set f double prime set f single prime equal to 1 over 0. So those are the two ways you can do it. Let's look at the undefined first, even though it is on the right-hand side. I want to look at that first. Okay, the only way that you can justify that is with the change that we've been talking about. All right, so for this one, you must state the change. And the change has to happen in f prime. So with an undefined, that's the only way to go. However, with a 0, there is an alternate way. You don't have to necessarily find the change in f prime. If you've got f prime equal to 0, then you know that there's a horizontal tangent. If there is a horizontal tangent, it must be sitting either above some kind of concavity or below some kind of concavity. So either it is sitting at the bottom, at the lowest point of a concavity section, or we know it's sitting at the top of a different kind of concavity section. And so if you just check the concavity, you'll know if it's a max or a min. A min will be sitting underneath what kind of concavity? Yeah, so f double prime is positive. A max is sitting on top of the opposite kind of concavity, negative concavity. So rather than checking for a change in the first derivative, sometimes it's easier to just check what the second derivative is. And then you know that that point is either sitting either on top of something or underneath something. That also can justify a min. And so you would say something like this. if f of a prime is equal to 0 and f double prime of a is greater than 0. So those are your two things you would have to say. If the first prime was equal to 0 and the second prime was positive, then a is a min. Because a minimum is sitting at the bottom of concavity. And then the opposite is true if a f prime of a is equal to 0, but f double prime of a is less than 0. So in other words, if this is concave down, then a is a max. I'll put quotation marks here around a since I used a as a variable and a as a antecedent, or whatever they call that in English. Okay. And so that is just another way, an alternate to proving the max or min, but I couldn't have told you that on the first day because you didn't know anything about concavity yet. Right? So now you know about concavity, so now you know a second way. You just got to decide what's easier. Do I have a chart? Well, then look at the chart and just say it's changing from here to here and then be done with it. If you don't have access to a chart, it's faster for you to check the second derivative than try checking the second derivative and seeing what that is.